welcome back to another video. In this one, we're going to continue with our PowerPoint. We're going to continue talking about the quantum model of the atom and how electrons ultimately behave as waves and as particles. But before we do that, I want to do a little bit of a review with you guys, just where we've been and where we're approaching with regard to the model of the atom. Now, way back when we first started talking about this, we talked about a man named Democritus, or Democ, my boy Democ, right? And he thought the model of the atom was pretty much just a sphere, just this little ball, this little atomic elemental atom ball, and that's it. No protons, no neutrons, no electrons, nothing. That's all he thought it was. And then we progressed. We had some experiments that were done. Aristotle came along and kind of pushed us back for, a good chunk of time. But we made it to a man named J.J. Thomson. J.J. Thomson! My man, J.J. Thomson. So J.J. Thomson did the cathode ray experiments, right? Cathode ray tubes. And he discovered, or pretty much noticed, that we had electrons, those little electrons. And those little electrons, little e's here in case you can't see it, those little electrons actually lived inside of the sphere that Democritus talked about. And Thomson said, well, if we have these little electrons, that this goo, the remainder of the sphere, must be a positive charge. And that was the plum pudding model, or the chocolate chip cookie model, whatever you choose. Personally, I like chocolate chip cookies. Not really a fan of plum pudding. It's not pudding, and there's no plums. Who does that? Anyway, so we got Democritus. We got J.J. Thomson. Then we came to Ernest Rutherford. And Rutherford took what he knew, and don't forget Dalton's atomic theory, and he came up with the planetary model. Because remember, Rutherford did the gold foil experiment. He found the existence of the nucleus, right? That nucleus with the protons in it and the neutrons. I'm doing pluses for protons and little circles for neutrons. And then he said the electrons don't actually live within the nucleus. They don't live with the protons and neutrons. They, in fact, live outside of the nucleus and orbit. They go around the nucleus, hence the term the planetary model. Okay? We're going to take what we've learned with these three models, and we're going to continue to develop our latest model, the Rutherford, the planetary model, into what we know with into a new model with the information that we've gained today. All right, so I will see you guys in just a minute. Hope you enjoy this. I'll let the music take us out. The music take us out, and I'll see you guys in just a minute. Take care, guys. Hey everybody, so just as a quick review, I just want to make sure you guys understand that when an electron absorbs energy, it jumps up in energy level. And when that electron falls, because it can't stay up there forever, it falls back down, it releases that energy. And that energy is in the form of a photon, okay? A photon of light. Now, the color of light, that depends on how far the electron is falling. If the electron were to fall, say, a greater distance, right? It's going to have a higher energy, which means the light will be of a higher energy. Violet, blue, purple. If the electron falls a lower distance between energy levels, it will have a lower energy. Red, orange, yellow, somewhere along those lines. So each energy fall that the electron makes corresponds to a specific energy, corresponds to a specific frequency, corresponds to a specific wavelength, which gives us a specific color. And we can calculate all this using our two equations, E equals HF and C equals lambda F. All right, so new stuff now. What type of spectrum is produced when hydrogen emits light? It is a bright line spectrum, very, very important. It is not a continuous spectrum. okay? Not a continuous spectrum. In fact, the electrons' energy levels, remember, they are quantized. Small, specific amounts. Just like when you're going upstairs. It is small, specific amounts every single time. The electron's energy is quantized. We just said that. Electrons can only absorb and release certain and specific quantized amounts of energy every time. Remember, guys, quantized. I will bring myself around this computer and I will say to you, it is quantized. All right, go back to the corner again. Let's see what else. So thus, only certain specific colors and frequencies of photons. Remember, a photon is a light particle. Only certain ones can be produced. All right, so here we go. The Bohr model of the atom. What's it going to look like? We got J.J. Thomson's model right there. We got Democritus's model over there. And then we got Rutherford's model right there. What's Bohr's model going to look like? Here it comes. It looks very similar to Rutherford's planetary model, but there's one major difference. Take a look at those electrons. See, on the planetary model right there, the electrons didn't move. They stayed in their energy level, right? This one stayed on this one stayed here, this one stayed here. But in the Bohr model, the one that you guys are looking at on the computer screen right now, in that Bohr model, the electrons are jumping between energy levels. Here's another one. The electron absorbs energy, it jumps up. It can't stay up there forever, so it falls back down, and when it does, it releases a photon of light. A photon of light. That's the Bohr model. So we've just progressed through Democritus's model. And then we went to J.J. Thomson's. Then we went to Rutherford's. Now you got the Bohr model. Don't say it's boring. No, it's the Bohr model of the atom. All right, so how does the photon that is emitted or the released energy correspond to a color line? It's a very good question. And we're going to see that right after this break. We're going to take a look at hydrogen. See you guys in just a second. Bye-bye. And we are back. Hey! So we're going to take a look at the hydrogen bright line spectrum. Now, looking at the hydrogen bright line spectrum, or the atomic emission spectrum, we see four, count them, 1, 2, 3, and 4 lines. We see a red line at 656 nanometers, a blue at 486, a purple at 434, and an indigo or a violet at 410. How do those 4 lines correspond to the Bohr model? The one where the electron jumps up when it's energized, falls back down, and when it does, it releases a photon of light. I'll show you. Those 4 lines correspond to 4 electron falls, we'll say. Each one of those lines, take for example the red one. The red one is being described or being shown because, or emitted because, an electron has fallen from the 3rd energy level to the 2nd energy level. The blue line, or the aqua one, is because an electron is falling from the 4th to the 2nd. The darker blue or the purple, the 5th to the 2nd, and the violet on the very end is the 6th to the 2nd. Now remember, hydrogen only has 1 electron. It's the simplest of all atoms and elements. So the electron is bouncing up very quickly, and it's falling down from all these different levels back to the 2nd energy level. And as it's doing it, it can only have 4 different falls, 6 to 2, 5 to 2, 4 to 2, 3 to 2. And it's emitting these 4 different bands of light. So when you look through the spectroscope in the previous video, you see those 4 lines when looking at hydrogen gas. Okay? So Bohr's model helped to give credence to this thought process that when an electron falls, it emits these lights, or these lights are emitted because these photons are emitted because electrons are falling down past energy levels. It's another diagram explaining the same exact thing. Moving on. So why are only certain and specific colors? Why are only those 4 specific colors produced? Remember, quantized, guys. Quantized. Small and specific amounts of energy. You don't have a continuous amount of energy, or else you would have a continuous spectrum, similar to the one we saw with an incandescent light bulb or sunlight. Thus, an electron can only absorb or release very certain and specific amounts, quantized amounts of energy. This is why we have the bright line or the atomic emission spectrum. We're going to skip over this next one, skip over this one. I will give you your homework. Always check your daily agenda. So, what did the Bohr model of the atom give us? It gave us three things, three very important things. Number one, it said electrons exist in stable orbits about the nucleus. Okay, they cannot be, just like stairs, right? You can't be in between stairs. You're either on the first step or the second step. Electrons are either on the first energy level, the second, the third, the fourth, the fifth, the sixth, or the seventh. They cannot exist in between energy levels. They can't be there. They cannot be there. Cannot be there. Nope, cannot be there. The second one, only certain orbits are allowed. Orbits or the energy level. So looking at the Rutherford model, this is an energy level or an orbit. This is an energy level or an orbit. This is an energy level or an orbit. The Rutherford model that I've drawn here has three energy levels or orbits. They mean the same thing. We're going to discuss in the future orbitals, but not yet. Not now. I don't want to confuse you guys. Last one's a little bit on the bigger side. I will move my picture around, hopefully. Whoa, just went up there. An electron passing from a higher orbit to from a lower orbit to a higher orbit must absorb light or absorb energy with exactly the same difference. Conversely, when it falls, it must release that energy. Think about it this way, right? I'm an electron. I'm down here on the ground state. I'm down here on the bottom. Boom, I just got hit with light. So what am I going to do? I'm going to rise up. I can't stay up there forever, though. I got to go back down there. So I'm going to fall back down, and when I do, I release a photon of light. That photon of light is what you see. Now, if I fall from way up here, my God, and I fall down to the bottom, I'm going to release high energy light. So if I fall from here all the way down to the bottom, that's going to have a lot more energy than if I fall from, say, here, and then I go down to the bottom. You're only looking at maybe half the amount of energy, or maybe here it's only a quarter of the amount of energy. So every time I fall from a different level, right, the most and then the smallest, my energy is changing. The degree of energy that I'm sending out, my frequency is changing, my wavelength is changing, hence my light, the photon of light that I release out when I fall changes every time with how much I fall. Hopefully that helps to explain it. If I made it more confusing, I apologize so much. So hopefully I didn't. All right, so there are some good points to Bohr's model, but there are also some downsides, and there are two shortcomings. One, scientists couldn't understand why electrons can only exist within those orbits. Why can't an electron exist here in the middle, or here in the middle, or here in the middle? It can only exist on those orbits or those energy levels? Why? And then the next one, it worked perfectly for hydrogen to explain those four lines, but it didn't really work for any of the other elements. So Bohr's model stepped us in the right direction, but there were still some shortcomings, and that's going to happen with anything. We're always going to have some shortcomings or some flubs, like some flub ups. So. All right, guys. Now, the exciting part, matter waves. Waves matter, but do matters wave? Waving. All right, so we're going to look at the wave-like behavior of particles, and more importantly, the wave-like behavior of electrons. Electrons! All right, Louis de Broglie.
De Broglie. De Broglie. De Broglie.
He hypothesized that any moving object, particle, will exhibit or is associated with a wave. For this hypothesis, he received the Nobel Prize in Physics in 1929. Now, electrons are moving. We know that from the Bohr model. They're moving up and down from energy level to energy level. So if they're moving, they must exhibit wave-like behavior. When confined to a space, waves can only have certain frequencies, certain energies, certain frequencies, certain wavelengths, certain colors. This supports Bohr's model, quantized energy. Yeah! Boom. This also supports that light has a dual nature and electrons have a dual nature. Electrons can behave like particles and waves. Particles and waves. Are you kidding? No, dead serious. Particles and waves. All right, I'm going to leave this video. I'm going to link this video up at the end of my video so you can see it. I want to just do one more slide, and then we're good for this one, guys. So every object has wave-like properties. So de Broglie's wave equation was this right here. Wavelength lambda equals Planck's constant on the top divided by the mass of the object times its velocity. For example, an electron that has a mass of 9.11 times 10 to the negative 28 grams is traveling at 90 miles per hour. It has a wavelength of 2 times 10 to the negative 5th meters. That is measurable in the IR spectrum. However, a baseball that is 0.15 kilograms and traveling at 90 miles per hour has a wavelength of 1.1 times 10 to the negative 34th meters. That is not measurable by any instrument. Now, be careful. That does not mean that it doesn't have a wavelength. It just means we can't measure it. But it still exhibits wave-like behavior. We're moving, right? When we move, we are giving off waves. We have wavelengths. Just because you can't measure them doesn't mean they're not there. And on that note, I'm going to link up a video maybe right there, right above me. Or maybe, wait, can you guys even see it? Man, I did it again. I put it right over my face. Well, guys, I'm going to try and see you guys. Wait, oh, why don't I just move me? Huh. All right, everybody. I will see you guys in the next video. Have a great day. Take care.